Hi guys, today we'll be talking about laser-induced breakdown spectroscopy, or LIBS. As you can probably tell, LIBS is a characterization method that uses high-energy laser pulses to atomize and excite particles in a sample. LIBS is unique in that it allows researchers to analyze and identify chemical compounds and biological materials in all three phases of matter without the hassle of sample prep. This makes it an ideal technique for on-site analysis of rocks, glasses, metals, sand, teeth, bones, weapons, powders, hazards, liquids, plants, biological material, and even polymers. LIBS can be performed at atmospheric pressure, in a vacuum, or even on other planets. LIBS is one method of atomic emission spectroscopy, or AES. The purpose of AES is to determine the elemental composition of a sample. The analysis can range from a simple identification of the atomic constituents of the sample to a more detailed determination of relative concentrations or absolute masses. Basic steps in AES are the atomization, vaporization of the sample to produce free atomic species, excitation of the atoms, detection of the emitted light, calibration of the intensity to concentration or mass relationship, and determination of concentrations, masses, or other information. Pulses from the laser are focused on the sample using a lens. For solid materials, a thin slab of the material is ablated. This slab is then further irradiated by trailing a portion of the laser to create a plasma of free electrons, excited atoms, and ions. At first, the plasma emits continuum radiation, but after some time the plasma begins cooling, which causes characteristic emission lines. It is important to time gate the detector to only observe the emission lines. Plasma light is collected using a second lens or in some cases an optical fiber. The collected light is transported to a frequency dispersive or selective device such as a spectrometer or SPE. Each firing of the laser produces a single LIBS measurement. However, by adding or averaging the laser plasma signals, the accuracy and precision are increased. Because the laser plasma is a pulse source, the resulting spectrum evolves rapidly in time. Additionally, multiple firing lasers can penetrate deeper into the sample and measure composition below the surface of a sample. Sample preparation for LIBS requires nothing. Little or no sample prep is needed to perform LIBS, and portable versions of this characterization technique can even be performed on-site. However, sample size is important because LIBS requires a minimum amount of mass in order to analyze a sample. The amount of mass required can vary element to element, but on average, the interaction volume, or the size of the excited sample for LIBS, is about 0.1 millimeters cubed. As we mentioned earlier, LIBS can analyze all three states of matters and biological materials. The flexibility of this technique makes it widely applicable to areas of industry and research. This technique is particularly useful in the metallurgical industry where it can be used to measure chemical compositions of alloys on site. Additionally, the Mars Science Laboratory mission used a LIBS camera in 2012 to characterize samples on the surface of Mars. However, like other atomic emission spectroscopies, LIBS is subject to operational parameters. These parameters include lens-to-sample distance, laser pulse power density, and the characteristics of the surrounding atmosphere. These factors can produce different spectra, making it hard to determine element ratios in non-standardized conditions. LIBS is good for microanalysis of small samples, but isn't very good at bulk materials, especially ones that are inhomogeneous. The interaction volume of LIBS is simply too small to get any useful information on the bulk material as a whole. Thanks for listening, and we hope you learned a lot.